Alright, so in this video I'm gonna be explaining another important article on graph representation which has a title Beyond Localized Graph Neural Networks, an attributed motif regularization framework. So this paper in 2020 we present InfoMotif, a new semi-supervised motif regularized learning framework over graphs. We overcome two key limitations of message passing in popular graph neural network. Localization. A K-layer GNN cannot utilize features outside the K-hop neighborhood of the labeled training nodes. And oversmooth, structurally indistinguishable representations. We propose the concept of attributed structural roles of nodes based on their occurrence in different network motifs. Independent of network proximity, two nodes share attributed structural roles if they participate in topologically similar motif instances over covariant sets of attributes. InfoMotif achieves architecture independence by regularizing the node representations of arbitrary GNNs via mutual information maximization. Our training curriculum dynamically prioritizes multiple motifs in the learning process without relying on distributional assumptions in the underlying graph or the learning task. We investigate three state-of-the-art GNNs in our framework to show significant gains from 3 to 10% accuracy across 6 diverse real-world datasets. We see stronger gains for nodes with sparse training labels and diverse attributes in local neighborhood structures. This paper proposes a class of motif regularized graph neural networks. So, localized message passing limitations that while they are highly expressive, the GNNs are inherently localized. Just the K-layer GNN cannot utilize features of nodes that lie outside the K-hop neighborhood. Also, GNNs with multiple layers learn over smooth nodes. So in this figure, you see the localized message passing limitations. For example, here B is more than 2 hops away from either A or C. C is in the 2-hop neighborhood of node A. One way to overcome these limitations is the paradigm of role discovery, that identify nodes with structurally similar neighborhoods. In contrast to the notion of communities defined by network proximity, structural roles characterize nodes by their local connectivity and subgraph patterns independent of their location in the network. Thus, two nodes with similar roles may lie in different parts of the graph. For example, two nodes with similar roles. They could be in different parts of the graph. For example, this node and this node may have the same role. So they will assign the same roles to node A and B with topologically identical local structure. So locally, the topology is the same. So that's why we say their roles is the same. And so we propose info motif. And these are three key contributions: that attributed structural role learning. We propose a novel concept of attributed structural roles. Also, architecture agnostic regularization framework. Also, distribution agnostic multi-motif curriculum. We propose two learning progress indicators: task-driven utility and distributional novelty, to integrate multiple motif regularizer within our framework. So the ELF layer follows this message passing role. And network motifs are a general class of higher order connectivity patterns with a history of use in network science. A motif has several topologically equivalent appearances in the network called motif instances. So a network motif is a connected induced subgraph consisting of a subset and a set of edges, and let K sub t be the number of nodes. We assume that the graph has a set of unique associated motifs. For example, M1, M2, M3, M4. These are unique motifs of the graph, for example. Let I sub t be an induced subgraph. We define I sub t to be a motif instance of I sub t. So we define I sub t to be a motif instance of M sub t if I sub t is isomorphic to M sub t. A motif M sub t can have several motif instances. While each such motif instance has a unique node set, two motif instances can share nodes. So we plan to use these local structural properties, for example, network motifs, to regularize the graph neural model during training. Typically, we train GNNs by minimizing the cross-entropy loss, where the this C index of the one-hot vector refers to the probability that we belong to the true class. Notice that the loss is agnostic to any local structural properties, for example, mixing patterns in social network that may be indicative of the true node class. Thus, we develop a modified loss, which we add this regularization that incorporates attributed motif structure. So attributed structure role learning. A K-layer GNN computes a localized representation for each node that incorporates information from its K-hop neighborhood. So we define its K-hop neighborhood, and X denote its set of input node features. Theta star is a function of X. So this is important. Single motif regularization that we introduce info motif, a framework to regularize node representations. We define attributed structural roles by assigning the same role to nodes that participate in motif instances over covariant sets of attributes. So most of the papers are either based on community or based on this role. In communities they use, for example, random walks, simple graph neural networks. But the roles, this paper is like this. We first adapt the base GNN representation specific to motif M sub t through a motif gating function, resulting in a gated embedding. Then we introduce a motif instance encoder to compute the instance-specific representation of node V conditioned on other co-occurring nodes. Finally, the motif-level representation summarizes the set of instance-specific representations through a permutation invariant motif readout. So for each node V, we maximize motif-based mutual information between its instance-specific representations. This is instance-specific representations, and motif. This is the motif-level representation. So we want the mutual information between them to be maximized. Highly dependent, these two random variables to be highly dependent on each other. So following neural mutual informations, we model as a discriminator network that learns a decision boundary to accurately distinguish between positive samples drawn from the joint distribution and negative samples drawn from the product of marginals. So we train a contrastive discriminator network D. This one is a contrastive discriminator network. The positive samples for the representations of motif paired with the motif level representations. The negative samples are derived by pairing with representations of negative instances. But do you really think this could be implemented in our brain? Our brain works much more simple than this. I mean, I don't think our brain uses that kind of contrastive learning that we do by augmentation and then those negative samples, positive samples in the way we do. All the brain does is just a simulation. It's just for example, Markov chain Monte Carlo is more similar to what our brain is doing. It's just a message passing, nothing else. And of course, the backpropagation in brain is very localized. It's not too long from two remote nodes to each other. So this is the algorithm. First, we initialize sample novelty weights, then supervised loss over labeled node set, then motif info max loss over entire node set. So we have different motifs, M1 through MT, and we have this input graph. So we give it to these graph neural network layers. It could be anything: graph attention, graph convolutional network. Then we have this base GNN representation. So using the self-gating unit, we get our representation, and finally node-sensitive attention weights. And we have supervised loss. But they also talk about skew-aware sample weighting. Prior work in curricular meta-learning has shown importance of reweighting training examples. So the novelty beta sub v of node v is a function of its motif distribution. For example, novel nodes contain uncommon motif types in their neighborhood, which in turn reflects in their attention weight distribution over motifs. So the novelty scores are normalized using the softmax function to give non-negative sample weights. Finally, this training. And these are the details. For example, for motif instance encoder, f attends over each node to compute attention weight alpha sub u. And they have motif gating. Everything is the same. Now, instead of readout, we have motif readout. Instead of discriminator, we have motif discriminator. And this is a sigmoid. W is trainable. And their results. You know, they compared with Node to VEC that I've explained in this playlist. I've explained Graph Sage in this playlist. Many of these things I've explained. So they compare and see that, for example, for Node to VEC, instead of 75 for just 20% of Cora data, they have 85. So it's quite a lot. And 80% here, you see 69. So it's a good improvement. For example, 80%, 88 for 60% of PubMed data. And this is node classification results. Using 10 random training validation. Info motif